Hello everyone. In this previous session, we have discussed about the LTI system, convolution of the system, their property, and the numerical based on this convolution theorem. And today we are going to discuss about the Laplace transform of the system. And in the class section, we have already discussed the Fourier transform of any signal. But there is some problem in Fourier transform because the Fourier transform is not possible for every signal. For example, we consider some signal here, e to the power at ut. When we draw this signal, it is an exponentially increasing signal. Okay, and this is the neither energy nor power signal. This is the neither energy nor power signal, and when we integrate this signal, this integration become infinite. And in Fourier transform, this integration should be less than infinite. Therefore, the Fourier transform of such signal is not possible. Fourier transform is not possible. In the second case, actually ut is mistakenly printed here. In the second case, e to the power minus 80, e to the power minus 80, sorry, e to the power minus 80 is converged, and for the time t tends to infinite, this magnitude become 0. But when we integrate this from minus infinite to infinite, their integration also become infinite. Therefore, the Fourier transform of such signal is also not possible. And third signal is the ramp signal. Okay, the integration of this ramp signal from 0 to infinite is also become infinite. Therefore, Fourier transform of all these three signal is not possible, or every signal which integration from minus infinite to infinite, if resultant to the infinite, then the Fourier transform of this signal is not possible. This is the problem of Fourier transform. To one example also is there. If e to the power minus 2t, this is exponentially actually decaying, therefore a transform is possible. But the second, if there is positive e to the power positive 4t, then this is exponentially increasing. This Fourier transform is not possible, as we discussed in above section. Therefore, this difficulty can be resolved by multiplying some signal xt with the convergent factor. Therefore, to obtain the Fourier transform of the signal, this signal first multiply with the some different signal which converts this signal or become this signal, result in signal which is absolutely integrable. For example, let us consider here e to the power 40. It is absolutely not integrable, but this signal is before the Fourier transform multiply with some convergent factor. Here we consider one convergent factor e to the power minus 7, and when we multiply this, then resultant become e to the power minus 3t. Okay, and when we plot this is the exponentially decaying signal, and then then integral of this e to the power minus 3t is less than infinite. Therefore, Fourier transform is exists for the signal. But one point should note here that this Fourier transform is only possible when this convergent factor, let us consider it with the sigma, is greater than 4. Is greater than 4. Okay. This is possible only for the sigma greater than 4. If the sigma less than 4, for example, when we multiply with minus 3t, okay, then resultant is e to the power minus t ut, and this is exponentially increasing, and again the integral of the signal is infinite, and the Fourier transform is not possible. Therefore, the Fourier transform of this signal is only possible when sigma is greater than 4, and this defined actually ROC of the Laplace transform, and this defines the boundation of Laplace transform where the Laplace transform exists, and after this boundary, the Laplace transform does not exist. Therefore, from this analysis, when we apply to the system and we take a Fourier transform of the signal, then we consider a general signal xt, multiply with the convergent factor e to the power minus sigma t, and when we explore or combine this signal, then the sigma plus j omega, as we know that this is the complex frequency and is equal to the s, then this integration becomes summation of minus infinite to infinite xt e to the power minus st dt, and this Fourier transform is nothing but the Laplace transform. Okay, then the Laplace transform is xs equal to e to the power minus infinite to infinite xt e to the power minus st dt, and here we got one point that the Laplace transform is Laplace transform of xt is nothing but the Fourier transform of signal xt multiplied with exponential minus sigma t. Okay, and the Fourier transform is nothing but Laplace transform evaluated on z omega axis, or when we put sigma equal to 0, when we apply here sigma equal to 0, okay, this sigma equal to 0, then the resultant is j omega, and this Laplace transform becomes the Fourier transform. Then our formula of Laplace transform is xx equal to minus infinite to infinite xt e to the power minus st dt, and then inverse Fourier transform we will discuss in the next topic or the later topic, but for today the xt equal to 1 upon 2 pi j exponential sigma minus j infinite and to the sigma plus j infinite xx e to the power st ds. Okay, our next topic is region of convergence. This region of convergence of Laplace transform is nothing but the define the region where the Laplace transform actually exists. As we know that the Laplace transform is nothing but the Fourier transform of xt e to the power minus sigma jt, and sigma is nothing but the convergent factor. Therefore, it is only possible when this integration is less than infinite. Okay, and when we move and consider their magnitude, then magnitude should be e to xt e to the power minus minus sigma t multiply with e to the power minus j omega t. Okay, and when we factor this into two parts, then this magnitude, as we know that their magnitude become 1, and the resultant Laplace will only depend on this magnitude xt e to the power minus sigma t. Therefore, the Laplace transform is possible only when this summation minus infinite to infinite xt e to the power minus sigma t should integral should less than infinite, and this defines the ROC of the Laplace transform, and here only sigma part defines the Laplace transform of ROC of Laplace transform. Therefore, when we resultant this, the xt is any general signal, but the this integral only depends on this function sigma t, and this sigma is nothing but the, when we explore the complex frequency is nothing but the j sigma plus j omega. It is the real part and it is the imaginary part. Okay, then for the sigma it is also written as the real part of S complex frequency. Real part of complex frequency is known as the sigma. Okay, therefore the range of sigma for which the Laplace transform converge is termed as region of convergence. Means the range of this sigma or real value of complex frequency S for which Laplace transform is converge, this is known as the region of convergence. Okay, this region ROC, region of convergence, consist those value of sigma for which Fourier transform of Fourier transform of xt e to the power minus sigma t converges. As we already discussed in the above section, this integral is this Fourier transform is only possible when this value sigma is greater than the 4, and this defines the ROC, because the Laplace transform or Fourier transform only exists when the sigma is greater than 4. If it is less than 4, then Fourier transform is not defined, and this is known as the ROC of the system. Okay, we move to the next. Therefore, the certain range of sigma for which ensure that xt e to the power minus sigma t is absolutely integrable, even though xt is not absolutely integrable. This defines the ROC. As we discussed earlier, e to the power 4t is not integrable, but we combine when we multiply with this convergence factor e to the power minus sigma t, and when the sigma is greater than the 4, this multiplication is absolutely integrable. Therefore, the range of sigma for which ensure that xt e to the power minus sigma t is absolutely integrable, even though xt is not absolutely integrable. Okay. Therefore, one question here. Next point is bilateral. It is known as the bilateral Laplace transform because we integrate it from minus infinite to infinite, and when we integrate it from 0 to infinite, we discuss in the later on. This is known as the unilateral Laplace transform. Basically, Laplace transform divided into two parts: bilateral and unilateral. Here our discussion based on bilateral, and later on we discuss the unilateral Laplace transform. Therefore, the bilateral Laplace transform, from bilateral Laplace transform we got a Fourier transform when sigma equal to 0, as we discussed earlier, and ROC only in the imaginary axis. Therefore, the Fourier transform, when we plot it, there is only a imaginary part. There is no any real part. Okay. If ROC of axis include, it mean from this analysis, it mean if the ROC means this is the Z explain, this is the imaginary part, this is the real part. If the Laplace transform exists when sigma is greater than minus 2, let us consider this minus 2, this and this, the right side of this property. Therefore, for this signal, it includes the imaginary axis. Okay. And for our discussion, if we put sigma equal to 0, then Fourier transform, this will result into the Fourier transform, and the Fourier transform, and the ROC when the Fourier transform, and then ROC is a single line on the imaginary axis. Therefore, this conclude here that if ROC includes the imaginary axis, therefore the Fourier transform x omega can be obtained by the replacing by the s equal to j omega. Therefore, we got a Fourier transform from the Laplace transform if the ROC include imaginary axis, and when we put s equal to j omega, then the Fourier transform is also obtained from the Laplace transform. Next topic is property of the ROC. Here the property is very important for the exam point of view. We will discuss here. The first property of the Laplace transform is ROC of Laplace transform SS consists the strip parallel to the j omega axis. Actually, when we draw one diagram here, and when x plane, when we consider here the x plane, it is a x plane, and in x plane, as we know that x is equal to sigma plus j omega, then this is known as the real part and this is the imaginary part. Okay, and for the previous analysis we know that the ROC only depend on the sigma, And when consider here, when sigma is greater than -2 or -3, then let us consider one value sigma is greater than -3, and then -3 this, and this region define the Laplace transform. Therefore, it is a strip line. Therefore, it is a strip line which is parallel to the imaginary axis. Okay. Therefore, the first property of ROC is consists the strip parallel to the j omega axis. The second is, if x is a rational, SS is a Laplace transform is a rational, then ROC must not contain any pole. It means when the rational, it means when x is something like this, s plus 2 divided by s minus 1 or something like this, and when we plot in the j omega axis the real term and imaginary term, for example here the pole is 1, okay, pole defined by first consider sx equal to s plus 2 upon s minus 1, okay, and when we draw it, s is equal to 1 for lower term, denominator is known as the pole and numerator represent the 0, and when we draw it here, the s is equal to 1, n is equal to 1, and the 0 defined with the this asterisk or the cross, and the 0 is s is equal to -2, will define this. And for the second property is ensure that when the ROC is something like that, and then ROC, if this is Laplace transform is rational means it is represented in terms of the numerator and denominator, then ROC means this section does not contain any pole, means in between there must not be any pole. We will discuss in the numerical section. Okay, the third property is, if xt is a finite duration, then it is absolutely integrable, then ROC is in entire S plane. Okay, we will discuss in the next section. And fourth property is, if this xt is a right-sided signal or infinite duration, then the ROC is the region of S plane to the right of the rightmost pole. It means when we plot it, if there is a right-sided signal like this, it is a right-sided signal, then their ROC must be right-sided or right-sided, this term. Okay, and the reverse of this is also possible happen. The next property, fifth, if the signal is left-sided and the infinite duration, then the ROC of this S plane should be left and leftmost pole. Left and leftmost pole means if the signal like this, okay, then their ROC must be this type, or it is a left-sided. Therefore, if the right-sided signal, their ROC must be right-sided. If the signal is left-sided, then ROC must be left-sided. And when we consider both, it means property of 4 and 5, then left-sided means the left-sided ROC, right-sided signal means the right-sided signal. If the signal contain both sided, means two-sided of the signal of infinite duration, then the ROC consists a strip of S plane. It means if the signal like this, left-sided and right-sided, then the signal left-sided represents left-sided duration and signal right-sided represents the right-sided signal. Therefore, the ROC should be a strip in S plane. This is the sixth property of the ROC. In this section, we have discussed how the Laplace transform can evaluate from the Fourier transform. We have discussed their analysis and their equation. Then how the region of convergence done, and how we obtain this, and property of ROC. and it is enough for the today's lecture. We will discuss on the next lesson. Thank you.